Hi, I'm Andrei. I'll be presenting our work on deep multitask learning for joint localization, perception, and motion forecasting. Recently, we have seen a lot of progress on multiple problems related to self-driving, such as perception, motion forecasting, and motion planning. Many of these methods take as input high-definition maps, which can provide a rich prior for these tasks. However, leveraging maps requires precise knowledge of the vehicle pose, which is assumed to be error-free by modern approaches. Like any other system, localization systems can fail unexpectedly. The natural question is then, how robust are state-of-the-art self-driving stacks to localization error? We investigate this problem by simulating localization errors on two state-of-the-art perception prediction and motion planning modules. We benchmark failures on the LP3 dataset. LP3 contains 1,800 sequences recorded in a large North American city. This is a subset of the recently proposed ATG4D dataset, which also includes appearance maps. The appearance maps are necessary to benchmark localization, perception, prediction, and motion planning jointly. For perception and motion forecasting, we simulate a misalignment between the semantic map and the LiDAR reading. The simulated lateral and longitudinal errors range from 0 to 80 centimeters and from 0 to 3 degrees in rotation. In terms of detection, mean average precision is fairly robust to translation error, but suffers a decrease of roughly 7% due to rotation error. In terms of motion forecasting, the mean distance between our predicted trajectories and the actual trajectories at 5 seconds increase by up to 30 centimeters for rotation error. For motion planning, we simulate a misalignment between the map and the output of the P2 module. We run the planner on the first frame and unroll the trajectory over 5 seconds. We observe a similar story. We see a much higher increase in collision rate at 5 seconds due to rotational error. Interestingly, the effect is less pronounced for the distance between the ego car trajectory and the trajectory chosen by the original human driver. We now focus on designing a system that performs localization and perception prediction jointly. We designed the system with 3 goals in mind. First, it should have low latency and ensure its computational cost is small compared to the overall perception system. Second, we would like to leverage learning-based LiDAR localization to achieve robustness to dynamic objects and intensity miscalibration, while also reusing computation from the perception side. Third, we would like our joint system to be easier to train and to deploy than its separate counterparts. The proposed architecture extends a state-of-the-art detection and multimodal motion forecasting network, the implicit latent variable model, with the ability to detect and correct pose errors with minimal computational cost. The pose estimation is done using a deep LiDAR matching approach over 3 degrees of freedom, x, y, and yaw, and the computed offset is then applied to the semantic HD map used in detection, forecasting, and planning. First, the perception system is trained by itself using ground truth object labels and pose information. Next, we freeze the weights of the perception system and train the localizer as a side module, leveraging feature maps from the perception LiDAR backbone. We benchmark our system on the LP3 dataset, focusing on motion planning metrics that measure both safety and similarity to a human driver. First, we show the performance of a system with perfect localization and how it degrades by introducing localization error just to the planning module or to both the planning module as well as P2. Although our system exhibits some amount of localization error, we see that we are able to match the performance of the ground truth pose system on all the motion planning metrics. Moreover, because we share computation between localization and perception prediction, we can run the localization subsystem in as little as 2 milliseconds. We now showcase some qualitative results highlighting the impact of localization errors on motion planning. The original trajectory followed by the human driver is depicted as a blue box outline, while the planned trajectory is the red box. Other actors are shown as black boxes, and their motion forecast samples from the first frame are the light blue boxes. Note that we run all of this in open loop, so we do not update their predictions, which is why they sometimes might appear behind them. In a normal setting, they would constantly be getting updated. On the left, we see the autonomous vehicle planning its trajectory under localization error, causing it to plan an incorrect and unsafe trajectory that can lead to a potential collision. On the right, we see our proposed multitask system capable of detecting and correcting pose errors, producing correct and safe motion planning behavior. To wrap things up, we show that incorrect localization can have a significant impact on modern autonomous vehicle perception and motion planning. We then proposed a multitask architecture to allow perception systems to detect and correct localization errors, demonstrating its effectiveness on a large-scale dataset. Please refer to our project website for additional information. Thank you for your attention.